I'll go ahead and get started. Hey, good morning, everyone. My name is Brian Stengel with KINBER, which is the Keystone Initiative for Network-Based Education and Research. Brandon Ross from TorreyPoint and I have, seems to be about 20 minutes to give you an update on an exciting project that we have underway here in the state of Pennsylvania. And it's very convenient that this NANOG is here in Philly. So we're going to be telling you a little bit about PennREN. So 3 years ago, a group of forward-looking individuals asked the question, why doesn't Pennsylvania have a statewide research and education network? We're only a handful of states across the country without an R&E network. As they look back at some of the reasons, some of the history, some of the failed attempts at putting together an R&E network for the state of Pennsylvania, one of the big ones was geography. Big state, a lot of mountains, a lot of bridges, a lot of rivers, tough to build in a lot of places in this state. Also a lot of issues with ILEX, state legislature and lobbyists, some typical issues with collaboration between state agencies, public and private concerns, and always ownership and control. So when the opportunity So this group here, sorry about this. So when this group saw the opportunity from the American Recovery and Reinvestment Act that put forth a good amount of money for the BTOP program, this group looked at it and said, let's come up with an idea for building a high-performance network across the state. So the group that started this right out of here at Penn, at our Magpie, which is the Internet 2 Gigapop, had some people from Penn State, as well as Three Rocks, which is the Internet 2 Gigapop out of Pittsburgh. So this group created the idea of the Pennsylvania High Performance Network, which is what it was called at the time. Once they got their legs under them and realized that there was a great opportunity to put a grant into the NTIA for BTOP, they then started to form a partnership, other relationships with other schools across the Commonwealth, and then rebranded, came up with a new name called KINBER. So KINBER is the organization of schools, of higher ed, state system, community colleges, healthcare institutions, economic development organizations across the state of Pennsylvania that are involved in this project. It's a member-driven organization with typical structure that you'd expect, board of directors, a 501c3, very member-driven and member-focused. So in 2010, KINBER was awarded a BTOP grant to build out PennREN. So KINBER's the organization, PennREN is the network. PennREN's mission, or excuse me, KINBER's mission will be to serve Pennsylvania through the establishment and sustainment of a high-speed R&E network across the state, connecting institutions of higher learning with K through 12, education, healthcare, workforce development, and other training programs across the Commonwealth. Some of the details, $128 million is the project. 99 of that is coming from federal stimulus funds. The remainder will be through matching. 48 strands of fiber are being built, 1,700 route miles, as well as this includes our fiber maintenance. The organization as it looks today, we've got the board of directors. We've got an executive director, Jeff Reel, out of Penn State. We've got a number of board committees or working groups with members from each of our institutions participating and contributing in the development of PennREN. We've also got an operations staff that will be hiring for some network engineers, as well as a project manager, compliance officer, and some marketing assistants as well. So the award for construction of the project was back in the end of last year. The organization that's building this network for us is Synesis, and their sister company Blair Park, right out of Philadelphia. They're subsidiaries of Quanta Services. Quanta Services is a large firm out of the Texas area. So Synesis is actually building our network. So this is the footprint for PennREN, the bow tie look. Each one of the segments around the state, each one of the stars denote what we're calling service nodes. The network will consist of rings in the east, rings in the west, and then dual rings in the State College area. PennREN will be a middle mile network. We are not going after last mile. So this middle mile network will be in place to allow our members to do the type of collaboration and the type of sharing that we believe they're not able to do today. Some of the services that we're contemplating at this point, while we don't have our service catalog created yet, we have our members and our working groups looking to develop what we expect to be a fairly comprehensive complement of services, dark fiber, dedicated Ethernet, connectivity to a shared R&E backbone, as well as some other services, possibly transit to commercial internet. With this, we're expecting our members to see a number of opportunities for collaboration that, again, it just has not been in place across the state to this point. The logical design of PennREN is based off of 13 service nodes that will be essentially the backbone for optical regeneration across the state. Each one of these service nodes will also include our active electronics, which Brandon will talk about here shortly. We also have a concept of access nodes. Our access nodes will be the points where fiber will be terminated and PennREN network will get to, but initially will not have any electronics. So our deployment strategy is to build out the backbone core network at these 13 locations. From there, last mile connections can be established for customers or members to connect to. We'll also be able to have other RENs will be connected to PennREN through service routing nodes. For growing the network out, we're expecting to exploit the fact that we've got the fiber in the access nodes and build onto it, allow our customers to access the backbone from our access network. So over time, we're expecting our members to benefit from the network effect. So who's building PennREN? Blair Park Synesis, again, is doing the 1,700 route miles across the state, doing all of the pole applications and right-of-ways. Majority of this will be aerial. There will be some underground for access into the sites for our members that will actually be colo hosting of our equipment. So Blair Park is doing that. Our members will actually be building out space in either their data centers or their telco rooms to provide us space, power, and cooling for us to put our cabinets and our electronics. Blair Park will also be doing the cabinets, installing, doing the fiber termination. And TorreyPoint is our partner for the design, implementation, integration, and all aspects of installation of the network. So with that, I'll turn it over to Brandon.
Thanks, Brian. I'm Brandon Ross with TorreyPoint, Network Architect, and like Brian said, I and the rest of TorreyPoint are responsible for the layer 2 and up architecture of the network. So this is a really exciting project for us, and it would be probably for just about anyone. It's only once in a lifetime that you really get to build out a truly greenfield network where you can kind of hope that you're going to do things right the first time. So we're really looking forward to implementing some new technology that hasn't been widely deployed, hasn't been deployed at all in some places yet. So one of the things that's new about the KINBER network is the fiber selection. It's OFS True Wave Reach Fiber. It has some pretty advanced capabilities. We expect it to be able to perform well for a very, very long time, and to be able to increase the bandwidth on it as technology improves dramatically over existing fiber selections. So we went over this a little bit, that it's a member-based organization. I think I pulled out some of these slides before. This might be an older presentation, but we talked about some of that. So we, TorreyPoint, when we replied to the KINBER RFP, we went in with partnership with ADVA Optical and Juniper Networks to build the network, which is a 15-segment network. You saw the map before of all the different segments. Each one of those segments is 48 strands. Total of 69 sites. That includes those access nodes that Brian mentioned, as well as the service nodes where active equipment is going. And the most exciting part is that as GMPLS develops, we fully intend to deploy GMPLS on this network, and that's really the most exciting part to us. Again, the network layout. So an example segment of this network, some places are a little bit challenging. Because of the desires of various members and the anticipated set of products that we're going to offer across this network, sometimes that requires multiple pairs to be used across any one segment to give different groups of institutions in the state of Pennsylvania their own kind of private network. So you can see here, this is just an example, but some red links that we're going to have to figure out how to resolve. In many cases, we'll have to go and figure out where to put in some amps or something. But there's a variety of ways to do it. But in either case, it's pretty exciting. At Layer 1, we'll be using the ADVA FSP 3000 gear, both 2 and 8 degree ROADMs, depending on the location. Raw-man amps were needed. And it's a 40-channel system, but the even more exciting part is that even on day 1, we're going to put in a single 100-gig link across the network. It'll start as a 10 by 10, but hopefully within a reasonable amount of time, we'll be able to go to 4 by 25 across that 100-gig link. Here's kind of an example layout of the engineering of one of the rings. You can see, I don't know how that text is big enough, but you can kind of see there are 2 degree ROADMs. Those are the blue dots in a lot of places. Green are the line amps, and red are the bigger multi-degree ROADMs. Those are generally in the 2 main locations in the center of that bow tie kind of design that you saw in the other diagrams. So just generally, ROADM, if you're not familiar with it, and I suspect most people here are, it gives us a lot of benefits over building a network in a more static way, because we can move resources around the network without having to move jumpers around and make other changes. But it helps us out also in power and dispersion planning as well. So how we architected the connection to routers, we have actually 2 different paradigms depending on the distance we're looking at on any particular link. In some places, we'll have gray optics fed into a transponder card, and the transponder, of course, takes care of the OEO and grooms the lambda to the right channel. That's where the distances are too far to drive directly from the router through, as we do in other places, within limits. In those places, we'll put tunable optics in the routers, and the lambdas are just carried as alien waves across the DWDM infrastructure. So just an example layout of one of the service nodes. These will be MX480 Juniper routers. We've arranged for the line cards, so we have line card redundancy, so we can put backbone links on separate line cards. So even if we have to replace a line card or if the line card fails, we're not going to lose the site off the network. And as far as routing nodes, we've designed 2 of them into the network as opposed to routing at every node. That's mostly based on cost. One at 401 North Broad and one at Allegheny Center Mall, and it was pointed out to me earlier that I have no idea how to spell Allegheny. But those will have the -R Juniper line cards that have the full routing table capabilities. And this entire network will be IPv6 from day 1. There's no question about it. Every node, everything will be on IPv6. So GMPLS, that's pretty exciting. Again, I think most people here are probably familiar with the concepts of GMPLS. The ADVA ROADM network will have full GMPLS across the DWDM infrastructure with the alien wavelength support. Of course, the control plane is standards compliant, and that's how we'll have the Juniper gear and the ADVA gear talk to each other to dynamically provision and tear down paths, both optical and layer 2 through the network. And the 100 gig link integrates into that nicely as well. So again, everybody knows how MPLS kind of brings the benefits, the good parts of circuits to IP. So I'm not going to go deeply over that, not in this crowd. But the most important aspect, we think, is fast reroute and being able to bring that down to the optical layer with GMPLS. And of course, it boosts our stability and performance and all that other great stuff. So I wanted to just go through an example of some slides that I stole from Juniper about how the GMPLS network looks like it's going to work as far as fast reroute. So one of the main things we want to do is protect against isolation of any particular node. And we want a 50 millisecond recovery time because that's the recovery time that Sonnet has trained us to want, right? So, but how can we do this with zero additional cost, right? We want to be able to put all this in without having to put in a whole bunch of extra optics and a whole bunch of extra lambdas across the network and then reserving bandwidth for this. So this is kind of a scenario of how that fits together. In this case, there's 2 core routers with GMPLS that are talking to the optical network, and it's a failure scenario where there's 2 fiber cuts in the network. So first we start, this is just our example network. It's kind of a similar network to what PennREN will be building. Of course, our first regular old path through the network goes through the top sets of ROADMs, and the backup path is through the bottom. The LSPs are built across that. So here's your standard fast reroute scenario. The dashed line is just your standard MPLS LSPs. So we get our first cut. Cuts the top fiber, just like, again, it's standard fast reroute. Traffic just flows across the backup LSP. But then what happens when we get the second cut? In most cases, we would be down for some period of time until someone got a chance to look at this in most networks, depending on how you've architected it. But in this case, since we're running GMPLS, we now signal a request from the Juniper router, or whichever router it is, up to the network to build a new optical path through the network to support this traffic. New path is built, and traffic begins flowing across that path again as it did before. Repair scenario is kind of the reverse of that. Once the first cut is repaired, you still can't use the LSP because the endpoints are still busy. We have to get to the second cut to be repaired, and then the traffic is moved to the LSP2 in a make before break manner. Then the old LSP is torn down, the optical LSP, and we can recover back to the way we were before. So kind of an example of that. Here's where we left off. One link is repaired. The link is noticed to be back up by the optical gear, and it turns that link back up. Notifies through GMPLS. Second link is repaired. That is then noticed. The LSP is rerouted back across that path. Now that that's working, we tear down the temporary LSP that we had through the third path, right, that we created through GMPLS. That returns to normal, and then we have back into the initial state where we have our standard fast reroute set up. Again, this is all brand new stuff. This is completely in the lab so far. The network is still under construction, and we're anticipating that these features will be available at or near around the time that we're turning up kind of maybe the third and fourth paths through the network so we can utilize this. Initially, as the network is built, there's only a limited amount of fiber, so we're thinking that the timelines converge nicely. Yeah, so just the point is that we can have all this recovery in the network without installing additional interfaces, without having to build a completely third path through the network, which gets our costs way down and increases our reliability. And of course, as in standard MPLS, each service node in the network, the active equipment nodes, are capable of building policy-based MPLS stuff across the network. You all know that. And this is just a summary of the features that we expect to implement in the network as they're available from Advent and Juniper. Again, not discussing dates yet, but we'll get there. So, as you know, the improved manageability and the improved performance and scalability and reduced costs are the reasons that KINBER and TorreyPoint work together to choose this model. And I'm hoping that, by the next NANOG, we'll have little bits of this implemented, and the program committee will be interested in us coming back to give an update on what worked and what didn't. Anybody have any questions?
Mics are open. Please identify yourself and your affiliation.
Dan Megorian, Johns Hopkins Applied Physics Lab. How's it going?
Good.
Yeah. So you're using directionless as well as colorless, right?
Correct.
For your restoration, right?
Correct. Well, we will. That's the plan. Remember,
Right.
none of this is built yet.
Right. Now, so your timers on GMPLS, your time for GMPLS restoration is a lot longer than your timers on the protocols, of course. So you are going to see an outages. It's not, none of that's 50 millisecond stuff. I guess it'll come back pretty quickly, but it's not going to be completely transparent. Things will bounce, right? So.
Yeah, you may very well be right. We haven't gotten that stuff into the lab yet to see what we could get the timing to be like. So
Right.
Hopefully by the next NANOG I might have a good answer to that.
Sure. And on 100 gig, are you building that on separate stuff without decomp, and then your 10 gig network is with decomp, or you kind of trying to put it all on the same one? And because normally with 100 you don't really use decomp. So.
I think that's still to be determined.
Is it okay? All right.
We're still working through exactly how we're going to do all that. So
Right.
yeah, don't know yet.
Okay. Thanks.
All right, mics are closed on this side.
Yeah, Martin Levy, Hurricane Electric. You talked about using aerial fiber versus underground fiber. Can you talk a little bit about what you expect quality-wise on 10, 40, 100 gig type services when you could potentially get movement on that fiber? Is that a concern for you guys?
Want to take that?
That's a great question. I don't think I'm really able to answer that. Certainly could try to talk to you offline about it.
So I mean, from my opinion, is it's kind of the standard answer of sure, aerial is going to be less reliable with the network layout that we'll have and GMPLS restoration on top of that. I think we'll be able to mitigate some of the risk.
I'm not so much worried about actual cuttage and a truck taking it out, for example. I'm more interested in dispersion and sort of movement of the fiber, which has been a concern at 10 gig and above.
Oh, I don't know.
Okay. Well,
I guess we'll find out.
yeah, leave it for some homework for you.
Yeah. Okay.
Okay, with that, we're
Thank
right on
you.
time. So Brian, Brandon, thank you.